The technical name for it is a residential load center, but people usually call it an electrical panel or circuit breaker box. This enclosed metal panel is usually built into an interior wall. It contains the circuit breakers that distribute, protect, and control the home's lighting and power. This load center consists of up to 40 circuits. Each one has 1 or 2 breakers. Each breaker powers several outlets in the home. First, a powerful press pounds a sheet of steel into what's called a U-channel. At nearly 3 feet long, 18 inches wide, and 4 inches deep, it's part of what's called the tub, the load center's main casing. A worker then attaches steel components made earlier called tub ends. A spot welding machine fuses them to close off both ends of the tub. Workers feed an aluminum strip that's 330 feet long and 6 inches wide into a stamping press. The press cuts the strip into 20-inch long segments called bus bars. It bends each bus bar 10 times, creating 2-inch segments called stabs. The breakers will later snap on to these stabs. Next, a worker inserts each bus bar into a plastic component called a base pan. The base pan insulates the bus bar. This prevents us from getting electrocuted. Another press then inserts a plastic rivet securing the bus bar to the base pan. The worker installs 2 components called neutral bars in the base pan. The neutral bars conduct electricity between the circuit and the wall socket. Next comes the main breaker. Its maximum capacity is 200 amps. Amps are the units of measurement for electrical current. If demand exceeds maximum capacity, it'll trip, meaning it'll turn off all power in the home. She makes sure it's sufficiently tight so that vibrations caused by street traffic won't loosen it. She also encloses labels to mark the breaker's pathways and an envelope with installation screws. Next, the worker puts the base pan assembly into the tub and secures the neutral bar with a copper bonding strap to ground it and prevent electrocution. She adds another component, one of 2 grounding bars. These ground each circuit. The breakers simply snap onto the stabs, making them easy to remove and replace if needed. Inside the breaker, several components interact to enable the flow of electricity. One is the load terminal, the entry point for the live current. A circular machine called Robot A assembles it and other breaker parts along its 16 workstations. Another breaker component is the bimetal assembly. It's an alloy of 2 metals and a magnet. It trips the breaker when there's an overload or short circuit. Next, Robot A welds a strip of silver which is conductive to what's called the contact arm. Robot A then positions the arm for welding with 2-inch long segments of braided copper wire. Copper because it's conductive as well as pliable. The robot fuses the copper wire to the contact arm and the bimetal assembly. The wire will flex with the arm to touch what's called the line terminal. This contact permits the electrical current to flow. Next, Robot A deposits the welded parts into the breaker casings called bases. This automated production line functions 24 hours a day, 5 days a week, and it produces a breaker every 3 seconds. Another machine called Robot B stamps the number of amps on each breaker handle. Then it connects a spring to link the contact arm to another part called the cradle. When there's an overload, the bimetal assembly causes the cradle to pivot and trip the breaker. Robot B deposits the spring and cradle into the base, then closes the base with a cover. This demonstration shows how moving the breaker handle triggers the mechanism that will enable the flow of electricity. If power demand exceeds the breaker's maximum capacity by 35%, the bimetal assembly trips the breaker and cuts the power. They cap off the load center with a metal cover called a trim. The warning label on it provides safety information and instructions. The load center is now ready for installation by a certified electrician. Enameling is the process of fusing colored glass to metal with intense heat. This decorative art developed more than 3,000 years ago. The earliest enameled objects archaeologists have found are pieces of jewelry made in ancient Greece. Today, artisans most often produce glass enamel on copper. Artisans handcraft these magnificent sculptures by fusing vibrant colors of finely ground glass to solid copper. First, the artist draws the design, then chooses the glass colors from a palette of hundreds of shades. She takes one element at a time and makes multiple copies of it on a sheet of paper. She has a lab produce a film negative, which she lays in an exposure machine. On top, she lays a silkscreen coated with a light-sensitive chemical. Then it exposes them to halogen light for 90 seconds. The film negative works like a stencil. Its dark parts block the light from hitting the screen, while its clear parts allow light through. Where light penetrates, the light-sensitive chemical reacts and hardens. The unhardened chemical rinses away, leaving just the image behind. In the next department, they lay the screen in a silkscreen printer. Apply chemical-resistant ink. Then load a sheet of solid copper about ½ millimeter thick. The machine automatically prints the images onto the copper. They cure the ink in an oven for 20 minutes, then repeat the entire exposure process for the backside of the sheet. Next, they feed the sheet into a two-step milling machine. It applies chemicals that eat away any copper that isn't coated with the chemical-resistant ink. This cuts out the shapes. Then it strips off the ink, which by this point has served its purpose. Now they have a blank shape, but it's completely flat. To give it dimension, they stamp it with a forming die. Now the enameling process can finally begin. For each color grouping of the design, there's an aluminum stencil. They lay down the first one and sprinkle glass powder in the first base coat color, which looks white now but comes out clear. Then a second stencil for the second base coat color, white. The shape then goes into a kiln for about a minute to liquefy the glass powder and fuse it to the copper. Once the base coat cools, they create the detail work with additional stencils and colors. This is where the true artistry comes in. Each shake of powdered glass is like a painter's brushstroke. Too much, and the color will come out too dark. Too little, and it'll come out too light. It takes an experienced enameler to get it just right. They craft dimension by blending colors and by combining different types of glass in the design. Some transparent, some opaque, some opalescent. After every few powder applications, they return the piece to the kiln, where the intense heat, 1600 degrees Fahrenheit, liquefies and fuses the glass to the copper. Slowly but surely, they turn what was a blank copper shape into a vibrant work of art. Meanwhile, an artistic welder skillfully creates the sculpture's metal framework. In this case, branches on which copper enameled birds will perch. He's using steel, but frameworks can also be made of copper, bronze, or brass. Besides birds, this sculpture features copper enameled leaves and flowers. Their stems are bronze because bronze fuses easily to steel. With the framework and background elements in place, it's just a matter of attaching the main design elements. Some industrial-strength hot glue does the trick. A modern twist on an ancient craft. These glass enamel sculptures make a glistening impression. The engine block is the largest single piece of metal in a car and also one of the most intricate. It houses and links all the engine components such as the cylinders and pistons, and it contains passages for circulating coolant. The engine block is where combustion converts into mechanical energy that drives the transmission propelling the car. Engine blocks used to be made of iron. Today, most are made of lightweight aluminum alloy for fuel efficiency. An engine block is a one-piece component cast from a sand mold. To make the mold, the factory mixes glue and a hardener with zircon sand. This combination of materials can withstand the intense heat of molten metal, but only for one casting. Each mold is made up of sections called cores that fit together. To make each core, a machine blows the sand and glue mixture into a master mold made of iron. It injects a gas that activates the hardener, which solidifies the mixture. This is the base core to which other cores will attach. The base core travels down an assembly line to receive the other cores. The next core molds the engine block cylinder bores, which will house the motor's pistons. A robot inserts iron liners into 6 holes in the core. They prevent the aluminum walls of the bores from wearing out from abrasion. The base core receives 17 other cores. The ones for engine block areas through which oil will flow are coated with talcum powder. This keeps sand particles from sticking to the aluminum and getting into the oil. The machines glue certain cores so they'll stay intact when the robots flip them upside down and attach them to the rest. These are the last 2 cores. The mold is now fully assembled and ready for casting. Workers load aluminum ingots into a device called an elevator bucket. It positions them above the jet melter, a gas-fired furnace. The bucket drops the ingots into the fire that's 1,500 degrees Fahrenheit, liquefying the aluminum. Just before casting, they heat the cylinder bore liners using high-frequency electric current. Aluminum will bond better to hot metal. They fill the molds from the bottom to avoid contaminating the metal with aluminum oxide. Oxide forms when molten aluminum comes into contact with the air. Pouring into the top of the mold would expose the metal to oxygen, and the pouring action itself would mix in the oxide. After the casting, the mold spends 6 hours in what's called a thermal sand reclaim oven. That breaks down the glue so the sand falls away. The heat also strengthens the metal. The cast aluminum engine blocks emerge, needing just some minor finishing. Robots turn them upside down to spill out loose sand. Machines saw off the risers, extra metal that fed the mold cavity to compensate for the 7% shrinkage that occurs when liquid aluminum solidifies. Finally, computer-guided tooling equipment performs a rough machining of the metal. This brings the engine blocks to a near-finished state. The engine plant that buys them does the final machining before installing the engine parts. Every engine block this factory produces passes through an automated vision system that inspects the engine block to ensure they have no defects whatsoever. The escalator was invented over 100 years ago as an amusement park ride. The moving staircase was soon equipped with a moving handrail for safety reasons. But those early handrails were driven by oily chains, leaving passengers with greasy hands. We get a cleaner ride on today's escalators, and if we want thrills, we try a roller coaster. An escalator's handrail moves at the same speed as the stairs. This makes the trip up safer because you have something to hold on to the entire way. To make an escalator handrail, a machine called an extruder pulls synthetic rubber up into it. A turning screw inside the extruder forces the rubber through a die, the way a pasta maker squeezes out spaghetti. 4 to 6 inch wide rubber strips roll out into a tank of water to cool because the heat from the extruder could alter their molecular structure. Now, the rubber strips move over rollers that are part of a mechanical measuring system. There's a little indicator on the roller that gauges the width and thickness of the rubber as it moves across. Over at the splitter machine, small round knives slice rubberized cotton the same width as the rubber strips. Then a mechanical puller unrolls material from 4 different spools. There are 2 streams of rubberized fabric, one stream of the synthetic rubber which came out of the extruder earlier, and one of rubberized cable wiring. They merge and stick together as they travel over a big steel roller. An unwinder peels away a plastic liner from the now 4-plied strip. Next, a worker places a piece of rubberized fabric and one of synthetic rubber on either side of the 4-plied strip. He presses everything except the strip of rubber around a U-shaped aluminum former. With a piece of steel, he bears down on the shape so the layers stick together. Then he brushes tack cement on the outside and pulls that piece of synthetic rubber at the bottom up around it. He folds the rim down, and using a hand roller, he seals its edges. Now the handrail has taken shape, but it's not strong enough, so a worker places it in a molding press. He positions a steel form inside the handrail so that it holds its shape. The top part of the mold lowers, and the handrail bakes under high pressure at 350 degrees Fahrenheit. 10 to 15 minutes later, the mold lifts, and a chemical reaction called vulcanization has occurred. The layers have been laminated, and the handrail is now strong enough. The last step is to trim away the flash or excess material. Here's the latest way to make an escalator handrail. A puller unwinds brass-coated steel wires from spools, drawing them along with thermoplastic urethane and polyester fabric through the dies of an extruder. What comes out is a strip of plastic-encased wires and sliders. The handrail shape passes through measuring devices that check its dimensions. Now they splice the ends of 2 plastic handrails together to form an endless loop. Using a roller, a worker presses the wires and plastic sliders of the inner carcass together. As he rolls, he blasts hot air into the splice with a heat gun. This softens the plastic so that it melds together. He covers it with a piece of thermoplastic urethane and again uses a heat gun to join the pieces. He wipes it clean with alcohol. Then he heats it up in a mold for a minute or 2. The spliced section melts together and then cool water hardens it. There's no seam line where the handrail could break. It's just one long continuous piece. And that's the inside story on the escalator handrail. Something to think about when you're on your way up. The job it does is exhausting. The exhaust system on your vehicle gets rid of harmful gases that could damage the engine. It also cleans up the gases a bit before venting them into the air. A properly functioning exhaust system does another big job, muffling the airborne noise of the engine. It's a system of metal tubes and plates we only seem to notice when it breaks down. And when it does, everyone can hear it. To make an exhaust system, a mechanical puller draws a stainless steel strip up into a punch press, shuffling it back and forth to allow for a precise cut with little waste. The press brings 60 tons of force to bear as it pushes the steel into a die. It punches out a baffle shape with holes in it which will form the skeleton for the muffler box. The finished baffles fall into a conveyor and go into a storage cage. Now, a long steel tube tumbles to automated blades which score the tube crosswise to prevent denting, and then cut it to produce smaller tubes that go inside a muffler. A circular saw descends on another tube to make a tailpipe. Its length depends on the type of muffler being made. A louver machine spins and punctures one of the inside tubes. The holes will regulate airflow in the muffler. A CNC bending machine grips and bends a pipe in several spots. This is how they make inlet, intermediate, and outlet tubes. These tubes run the length of the exhaust system. Then they place a tube in a circular hydraulic vise, which pinches the end down to a prescribed diameter to allow for further assembly. A worker now places two baffles in a jig. He fits the tubes through the holes in the baffles so that the tubes connect the baffles. 3 mandrels slide into the tubes. The mandrels expand, locking the tubes to the baffles. Then they contract and slide out. Now the baffles and tubes are one piece. Next, a robotic arm picks up metal sheets which will become the outer skin of the muffler box. It pushes them under an oval mold. Another arm with numerous rollers on it moves up and wraps the steel around the oval form. Then a metal block moves over the ends, double folding them. This locks them together, and it completes the assembly of the muffler's outside skin. Magnets pick up the new skin, and sliding on rails, they relay it to a mechanical claw, which in turn feeds it to a flanger. The flanger bends the edges, creating a lip on either end of the muffler skin. A carousel turns, and a mechanical claw transfers the newly flanged muffler skin to the stuffing position. Hydraulic pushers press the pre-assembled baffles and tubes inside the skin. After the muffler is stuffed, the robotic claw transfers it to a conveyor belt. Next, a worker presses each end of the muffler against a set of steel expansion fingers. The fingers move forward into holes in the muffler. They expand and lock the baffles and tubes inside to form one solid internal unit. Grippers place the muffler on a spinning machine that will fasten the caps on. Rollers press against the flared edges of the revolving muffler, tightly locking the end cap to the rest of the body. Here you see the rolling in slow motion. It takes only a few revolutions to do the job. Then the roller backs away, and a mechanical arm grabs the muffler and transfers it to a conveyor belt. Now these mufflers are ready to help keep the traffic noise at a minimum. It's pink and fluffy, and it keeps us warm. Fiberglass insulation is a great way to prevent heat loss from our buildings. It has a woolly texture, but it is, as the name suggests, made of very fine threads of glass. That's why it's sometimes referred to as glass wool. Fiberglass insulation will reduce energy consumption, but it also reduces waste because it's made from at least 35% recycled glass. The recipe also includes what's called the batch, a lot of sand and smaller portions of soda ash, limestone, and other minerals. The glass, called cullet, used to be bottles and windows. This will be its second recycling. The cullet and batch ingredients spill onto a conveyor belt system, which transports it all to an electric furnace. The conveyor moves back and forth to evenly distribute the cullet and batch ingredients. They seep down and melt into a previous mix, which is now a pool of glass at the bottom of the furnace. The glass liquid now flows out of the furnace and into sloped channels. Inside these channels, the temperature is kept red hot by natural gas burners. This keeps the glass mix in a liquid form as it oozes out of the holes in the bottoms of the channels. The melted glass falls about 3 feet into a spinning bowl. It's called a fiberizer. The spinning action flings the glass through thousands of holes in the bowl, creating thousands of feathery glass fibers. Gas and compressed air pull the fibers, stretching them thinner. The process is a lot like making cotton candy, and the spun glass even has a similar texture. But the fibers will soon become even more like cotton candy. Nozzles spray them with the polymer glue tinted pink. The now pink and sticky fibers drop into a hole in the ground and amass. Then a conveyor belt takes the mounds of sticky glass to an oven. Steel plates compress the pack as it enters the oven that's heated to 500 degrees Fahrenheit. Hot air blows through it, setting the glue. As the pack exits the oven, circular saws cut through it, making 15 to 24-inch wide strips that are called lanes. The lanes pass by a series of poles that push them apart. Next, an inkjet brands each lane with a number that conveys the R value. R stands for resistance to heat flow. It's a measure of how well the insulation will stop heat from going through the roof, and your energy bill along with it. A chopper with big steel teeth now cuts the lanes, making chunks that could easily be installed in an attic or wall. After chopping, the conveyor belt accelerates, transporting the fiberglass bats to the next station. A few at a time, the bats plunge down a chute to a mechanical arm which slides the bats into a compression chamber. There, a hydraulic ram squishes the bats down, reducing their bulk 5 to 10 times. This compaction will make them easier to transport. Now, another ram comes from the side and pushes the stack of compressed bats forward into a spout. The spout is a hollow bat-shaped frame. A worker pulls a plastic bag over it. Then the ram pushes the fiberglass insulation bat into the plastic bag, and the process begins again. A conveyor belt transports the bat-filled bags to a machine that heat seals them. Then they're sent off to be installed.